Welcome everybody to the 14th Wi-Fi 6 tutorial from octoScope. Today we will be discussing traffic generation in relation to Wi-Fi testing, and we'll be covering multi-perf octoScope's traffic generating in quite a bit of detail. My name is Janne Linkola. I'm the Senior Director of Marketing here at octoScope, and actually now at Spirent since octoScope was acquired in March. I've spent most of my career at various kinds of roles at operators, usually something to do with Wi-Fi, although I started my career in cellular. Most recently, I worked for AirTies, one of the leading consumer mesh vendors in the space. I'm joined today by two colleagues. Steve Shearer is the chief scientist here at octoScope. He has just a really extensive background in the telecommunications industry. He worked for Philips in the terrestrial radio systems area for many, many years, working on systems like GSM, TDMA, CDMA. Was involved in various kinds of R&D and standard activities. We hired Steve from Wi-Fi Alliance, where he led some LTE and Wi-Fi coexistence activities. He knows Wi-Fi technology really well due to his background in Wi-Fi Alliance, and is also very well versed in RF area. Really, my go-to guy in that space. All the demos in this tutorial are performed by Nandini Venkatraman. She, I would say, is probably one of the few top leading experts as far as the Octobox test bed is concerned. She really knows it in and out, and she's gained this experience through performing testing here at octoScope. She's been doing it for 5 years. She's led the methodology, the test cases, test script development. She finds most of the bugs and is a really busy person. So we're quite happy to have both of Steve and Nandini today in this tutorial. As I mentioned, we'll be covering traffic generation. So here's a few features that you really want to look for when you're shopping for testing systems. You want a system that is capable of doing multi-point to multi-point traffic generation. Why? Well, because real world is multi-point to multi-point. In order to troubleshoot any kind of issues that you find, you need a lot of statistics, metrics, tools to help you in troubleshooting. Multiperf has an out-of-band management capability, and this is a really cool feature because it allows an interactive way to use the test bed where you can perform the test and see immediately the results. A lot of systems out there are sort of, the system goes blank for 10 minutes and then you see the results, and the important thing happened 5 seconds into the test, and you lost a lot of time. You want a system that is able to recover from link disconnections. Why? Well, because they're quite a common occurrence in the testing scenarios that we run. Of course, timing is important for things like one-way delay measurements, and if you're doing sniffer captures, you want to make sure that the time is captured correctly. Of course, most testbeds have various kinds of traffic emulation capabilities, but you also are going to want to find a system that is able to bridge real traffic into that testbed. And of course, it's important to find a system that has a lot of coverage in different kind of devices under test. So the test client is ported into various operating systems, and of course, if you can interoperate tools like iPerf, that's even better. So with that, let's go each area in detail and how multiperf facilitates this. I already talked about the multi-point to multi-point capability. This is, of course, how the real world works. You might have a home where one person is browsing the internet while another person is printing something on the printer, maybe accessing something on a file server in case of let's say an office or an enterprise application. Especially in networks where there are multiple nodes, for example, mesh networks. This is actually an important area of the optimization. How do the traffic flows exactly get mapped into various nodes? How load balancing works, backhaul, front haul. You want to make sure that on the traffic generation side, you're able to emulate what would happen in the real world. And the reason I'm emphasizing this is that a lot of systems don't do this. Due to various test instruments constraints, we often see systems that can only do point to multi-point systems. And of course, in the octoBox test beds, everything has been designed from the ground up with multi-point to multi-point in mind. As I mentioned, we have Nandini here for all the demos. We'll be doing a lot of demos today. They are all going to be done with this test bed here. It's called the Stack Max. It is octoScope's most fully featured test bed. As you can see, there are 5 chambers in the system, the 5 open doors here. 4 of them have space for you to put devices on the test, whether that's access points, mesh networks, or phones, or what have you. One of the chambers here, called the PAL box, is full of test instruments. As you'll see, this is another way to view that same test bed. Again, we have these 5 blue squares here representing the 5 chambers that I talked about. This square here is the PAL box. You'll see that what I've done here is I've highlighted with red color all the test instruments that are embedded in the test bed. And as you'll see, they're in every chamber in the test bed. So you'll be able to involve any of these instruments in a number of different traffic flows. So it's really quite capable to facilitate almost any kind of traffic flow scenario you have in mind. You'll notice that the test instruments have 2 different names. There's something called the PAL6E. This is a test instrument built on the Qualcomm Hawkeye Pine platform, and it is capable of emulating both access points and stations. We also have instruments called StayPals. These are built on the Intel AX210 platform and are able to do station emulation. So with that introduction, let's go to the first demo. Here is Nandini, and she'll show you some multi-point to multi-point demonstrations.
Yanni mentioned that I will be using the Stack Max for a lot of my demos. This is a photo of the Stack Max. It's got the embedded devices in each chamber here, here, and here. And this is the PAL box that has 16 StayPal devices. I'm going to be using some of these devices in my demo going forward. So the first capability I'm going to show is the multi-point to multi-point traffic generation capability of multi-perf. I'm going to set up 2 traffic pairs. So my first traffic pair, I'm going to set up this PAL6E as an access point. PAL6 devices are configurable devices, so you can configure them as APs, stations, sniffers, inline sniffers. They can also support virtual stations up to 64 per radio. So the first traffic pair is going to be a PAL6E set up as an AP, and I'm going to run traffic to an Android phone, which is running our latest Android multi-perf. The second pair is going to be an ASUS AP that's in the box 38 chamber. It's going to be part of a link with one of the StayPals that's in the PAL box. I'm going to run traffic to the first traffic pair first, and then introduce the second one to show some interesting capability that multi-point to multi-point can help you with. So this is our new software release. I'm going to introduce this before I start my demos. So on the left-hand side, you have configuration for all of your devices. We have all our attenuators here. We have our MPEs, multipath emulators here. We have the turntable here. We have our traffic pair configuration here. There's two modes. We have dashboard mode and auto test mode. Dashboard mode is a mode where you can control the attenuators and the turntables and play around with everything in the system. And once you have everything set up the way you want to, you're getting max throughput and everything, you can save it as an auto test. So you can save it as an RVR test or RVOVR test, which will give you our polar plots. We also have sniffer configuration here, so you can start and stop sniffers. I have two sniffer probes here, so I'm going to be showing that demo a little bit later. And you have our instrument configuration as well. So all our PAL6s and our stay PALs can be configured from this panel here. Going back to dashboard, and then in the middle of the screen, you have the graphs. So you've got the status of all the attenuators in the system up top, and you've got statistics, real-time statistics coming from all the PAL devices. They report their own statistics. So there's a bunch of statistics that you can pick and choose from reported by the chipset, and you can have graphs on either side of the screen, and you can enable, disable based on what you want to see on your screen. On the right-hand side, we have status for all the devices. So you can see which ones are up and associated. You can also use this as a legend for the plot. So you can turn off and turn on statistics for the device that you want to see on the plot. The statistics for each device matches the color of the endpoint that you see on the right-hand side. So for the first demo, I'm going to turn off the devices that I don't need here. But I'm going to start traffic between the PAL6 AP and the Android phone. So you've got traffic going there from the PAL6 AP to the Android phone. The traffic, you can see the statistics coming from the PAL AP, reporting its MCS, data rates, and bandwidth. Now you can see about like 500 to 600 11AC traffic coming from the phone. What I'm going to do is I'm going to introduce the second pair, which is on the same channel. So it's going to throttle this traffic, and we'll see how the phone handles that. So that's my second traffic pair. That's going to introduce my 11AX stay PAL device. And you can see the effects of contention here. So you see that the traffic to the phone has almost dropped off. The traffic here takes the color of the receiver endpoint. So you see the blue traffic comes from the phone. Now the traffic to the stay PAL throttles the phone traffic, and the traffic to the phone drops off. If we wait a little while, we'll start to see the traffic to the phone slowly recover. You can see that it's kind of nudging along and doing some trickle traffic, which takes away from the traffic. So some interesting effects of contention in the AirLink. And you can actually see all of this data on the screen with throughput and statistics together because of multiperf, because you're able to run multi-point to multi-point traffic using multiperf.
Thank you, Nandini. So as you already saw, the Octobox UI, especially the new software UI that Nandini was demoing there, offers quite a bit of tools for troubleshooting your test cases. And that's really important, obviously in the case where you're not getting the result that you might be expecting. In Wi-Fi, the user experience is the end result of the interaction of a lot of adaptive parameters in Wi-Fi. There's quite a bit going on there. And so it's important to have tools to analyze what's going on. And the multiperf tool offers quite a bit of these tools. First, on the application emulation layer, layer 3 through 7, multiperf itself is able to give you various kinds of statistics, things like, throughput, delay, jitter, packets lost, packets resent, that sort of stuff. If you involve the PAL test instruments that we talked about earlier, then you'll be able to see Wi-Fi layer 1 and layer 2 statistics, these things here on the right, for further understanding of what's happening in the Wi-Fi layer. And of course, the testbed also enables packet capture, wireless packet capture through a feature that we're going to talk a lot more in later on, but we call it sinker sniffing. So now you see all the packets, and that's really the ultimate troubleshooting experience. I should mention a feature that we have coming up later this year based on the packet capture. We're currently developing a feature where we are essentially recreating these layer 1, layer 2 stats based on packet captures. And what that allows you is you no longer have to have an octoScope PAL test instrument as a traffic endpoint. You can, for example, have, an iPhone against, some off-the-shelf access point, maybe an access point that you're testing. And as long as you involve a test instrument to sniff the packets, then we'll be able to give you these statistics. This same feature will allow a really cool user experience that we call cross-probing, which is, imagine this being, this image here in the left being the plots that have been recreated using the sniffer capture capability that I just talked about. And let's just say you're interested in this area where a lot of these parameters are sort of dropping quite dramatically. You'll be able to double click any of these plots at a particular point of interest, and the user interface of the server software will take you into the packet capture to that point in time, where you can do further troubleshooting. And of course, you're able to come back to this UI, back and forth. So this will be available in fourth quarter. It looks like there might be a question.
In the diagram, was there a signaling tester or non-signaling tester? And if it's the latter, what dependencies are there for an APUT or STAUT, which is a QC and Intel likely provided DLLs, but custom DUTs may not?
Let me try to take that one, guys. So our system is signaling. It's all signaling. It's really running the test through either your device under test, which we expect is signaling, or endpoints could be our instruments PALs. They can be your stations, or they can be, when they're at access point, usually the endpoint is bridged to our server on Ethernet. So you run through the access point as a bridge. So it's all signaling. Having said that, we have customers that are in the early stages of chipset design that will not have signaling implemented. They have usually test modes. They can generate their own traffic on their own DOT. And we have some tools, like we've got Triathlon that's married to the light point to help you evaluate that. I hope that's helpful. If not, feel free to speak up and we can discuss. But for the time being, just assume everything here is signaling.
Let's go to our next demo. Here's Nandini again to show you some throughput analysis on the testbed.
So For the second demo, I'm going to be using a station that's in the PAL box, one of the 16 stations that's in the PAL box. And I'm going to be running traffic to the AP that's inside the box 38 chamber. Now, I'm also going to introduce some variations using the attenuator, the multipath emulator, and the turntable. So with the attenuator, I'm going to increase the attenuation. So we'll see changes in RSSI, and we'll see how that affects throughput and the underlying statistics. And with the multipath emulator, I'm going to be introducing multipath in the link, so we can see how that affects it as well. And then towards the end, I have a fun demo with orientation with the turntable. So going back to the software, I'm going to be running traffic between the AP and the StayPal that's inside the box 38 chamber. I'm going to hit start there. We see about 1800 megabit per second coming from the StayPal. From the ACP to the StayPal, this is 11AX. 2x2, we have 160 megahertz bandwidth, MCS 11. Everything's at max rates, max throughput right now. Now what I'm going to do is I'm going to introduce some attenuation here using the attenuator that's available in the MPE. So you see the status of the attenuation coming up. And you see the corresponding dip in throughput. Now, because there's a throughput dip, you'll start to wonder why, and you can see the reason why. So there's a 20 dB drop in RSSI, and there's also corresponding adaptation behavior seen in MCS. Bandwidth is still holding steady at 160 megahertz because it has dropped MCS to adapt to the new signal levels. Now I'm going to introduce multipath. So I'm just going to introduce the multipath element by turning that switch on. So you see that because I introduced multipath, there is a further RSSI drop. There's a throughput drop, MCS drops, and now bandwidth has given up and dropped to 80 megahertz on the TX side. So you can actually turn off TX and RX to see which one actually adapted down. So that was TX rates adapting down. But what I can also do is I can go back. So I'm going to turn off the switch and go back and remove the multipath. So you can see if things adapt back up to the original levels. And I can also set my attenuators back to 0 dB. You see that they've gone back to 0. Now things are back up to max rates and max throughput. But you can see here that, you know, while adapting back up, MCS chose to stay at MCS 9 in one direction for a while before it came back up to MCS 11. So this is the kind of adaptation behavior that you can see using the statistics that are reported, as well as using the octoBox testbed to control the attenuators and the multipath emulators. Another thing that we have is the turntable. So on this system here, I have the AP sitting on top of a turntable. So I'm going to turn the turntable for this demo, and we'll see the effects of rotation on throughput. So I'm just going to turn very slowly. So you see the turntable turning, and you see the effects of rotation on throughput. And you can also see why throughput is dropping. There are MCS drops, and there are variations in RSSI caused by rotation. So the turntable is going back and forth. And you can see the changes in all the statistics caused by changes in orientation for the device under test.
Thank you, Nandini. Looks like there's a couple questions here before we continue. The first question came from Matt. He's asking, shouldn't multipath improve throughput rather than reduce, as we saw in Nandini's demo? I think Fanny and Steve and Nandini, feel free to jump in as well. But I think the short answer is that yes, multipath would give you multiple paths, and so MIMO, of course, requires multiple paths in order to operate. So if you're in a situation where you don't have enough paths, then multipath could potentially improve it. However, in that particular case that Nandini was running, we already had multiple paths in there. So we didn't get any path improvement from the emulator. Instead, we got the other impacts, which have to do with, signal summing in weird ways. And so we effectively saw an MCS adaptation behavior.
Yeah, that's actually a good answer. I would maybe just add to it. So multipath, there are aspects of multipath which are directionality. So when the signal comes from diverse directions, that improves your throughput. MIMO requires that if all your signals come from one direction, they will be a single feed. To get multiple MIMO streams, they have to be spatially diverse. And so let's say in a house, you have signals reflecting off walls coming into the one side of the device and into the opposite side. That helps the multiple MIMO antennas pick up different streams and resolve the signal into multiple streams and gives you spatial multiplexing. That's just directionality. Now, multipath also has nulls. So when you have these reflections, you may have standing waves. When you have standing waves, they cancel each other and you get a null. And so if you look at multipath signal, you get these sharp, deep nulls versus frequency. At the frequencies where you have when you have that resonance with the reflections depending on house and its sounding. So the nulls in the signal and the directionality are caused by reflections. So what I think, Yanni, you're saying is we already have spatially diverse signals, and that comes from the way we hang antennas around the device. We have that spatial diversity. To it, we can add the nulls using our multipath emulator or MPE to create this realistic multipath. But the nulls never help you. I mean, they almost never help you because they take away your power. So the spatial diversity of multipath helps you, but the nulls hurt you. And so that's what you are seeing in this demo, the impact of those nulls alone, not of spatial diversity. I hope this makes sense.
I think it was an excellent answer. All right. Very good. Matt continues here. What about latency? Any changes in how you measure latency in the new system? Yes, absolutely. Yes, we're going to talk about that actually later on, but sneak preview, there's now an ability to measure one-way latency, whereas we could only do round-trip latency until now. Let's move on. So something I want to talk about. So we've seen now a couple demos already. Nandini is showing, she's manipulating all the dials, the traffic is impacted by, how she controls the test bed. We're seeing all this rich visualization on the screen. The cool thing I want to really emphasize is that we can do all that visualization without impacting the measurement itself. The measurement and the control and reporting on the measurement are fully separated in the octoBox test beds. We do that, we essentially have multiple 10 gigabit backbone Ethernet networks there. One is dedicated purely for the traffic, as I said. There's another one where all the control, orchestration, starting of flows, stopping of flows, reporting on all those statistics. Also, any sniffing is happening in this network that we call the management network. In fact, there is also a third network for accessing the test bed from the outside with a web browser. So the fact that we're seeing the web browser UI, that doesn't impact the measurement either. All right, but anyway, let's talk about disconnections. These are a very common occurrence in wireless testing. In fact, they are kind of the point of a lot of different kinds of tests that we end up performing. We oftentimes are interested in some behavior, some adaptation as we increase the distance from the access point. And often those tests are ran until you actually get a disconnect. We're interested in finding where that point of disconnection is and that user experience adaptation behavior until the point of disconnection. So that's like one way that we see them. But of course, there's also things like handovers, either between two access points, or maybe we're looking at handover between Wi-Fi and cellular connection. And of course, these handover areas and events are an area of optimization in our industry. So of course, we need tools that can characterize and survive these disconnections. Multiperf recovers from these using the mechanism that I just described, right? There's two backbone networks. So even if we lose connectivity on the traffic network side because we've emulated a very long distance in between two nodes, we still have an always-on management connection, monitoring the status of all those test instruments and devices. And so the moment we recognize that the physical connectivity is regained, we can then automatically reestablish all the relevant traffic flows that were in place. All right, let's talk a little bit about timing. It's, of course, is another super important thing, especially in a test bed like the octoBox, which has all these different chambers and test instruments here and there. And so we want to make sure that we're getting all this reporting, all these sniffer captures from a single time domain. Why? Well, the user experience is often quite sensitive to little differences in timing. So we want to make sure that we capture it correctly. And so we can correlate events, what happened before, what after, and things of that sort. And of course, we're achieving that in the octoBox test beds through precision time protocol that we run in that management network that I was talking about. Let's go to another demo here. Nandini has prepared a handover demo for us.
All right. So Yanni was just talking about disconnections, and I think the best way to show a disconnection test is a handover test or roaming test. So to do this demo, I'm going to set up this PAL6C that's in the PAL box as AP1, and I'm going to use the second PAL6C that's in the smart box here as AP2. Both of these PALs have attenuators to them. So there's an attenuator here, and there's attenuators inside the multipath emulator. I'm going to be controlling both of these attenuators to cause this station to roam between AP1 and AP2. This station is an Android device. It's running our newest Android multiperf. So it's got the out-of-band management that Yanni was talking about, so that when the station loses connection, we use that management network to ping the device and pick back up when it connects to the next device. Now, another thing is I mentioned earlier that the PALs can be inline sniffers as well. So I've set up both of these PALs as AP inline sniffers, so we can actually look at the handover event using a sniffer capture. So I'm going to start my traffic, but before I do, I just want to introduce the two APs here. One's my green AP, which is my PAL6B_5 here, and PAL6C_5 is my orange AP. So this guy is AP1 and this guy is AP2. You see statistics coming from both of them, control traffic coming from both of them. So I'm going to start the test. So there's your traffic coming from the phone to the AP. And you can see statistics coming from AP1, which is your orange AP here. So the phone is right now connected to AP1. You can look at the status and see the associated devices to the phone. I'm going to introduce some attenuation in the link using the attenuators. And I'm going to disconnect the phone from the AP that it's connected to. I'm also going to start my sniffer here. And I'm going to decrease the attenuation on the second AP. So you see that now your traffic's coming from the green AP. And then in the sniffer captures, traffic is now coming from PAL6B, which is my green device here. Now because of the precision time protocol that we have, everything's time synced in the system, and we see the sniffer captures, the packets coming in the sniffer aligned in time. So now I'm going to roam back between PAL6B and PAL6C. So I'm just going to kill the link here. And I'm going to open up the link here. So now you can see that things are coming back up on the orange guy. And you see all the control messages going to PAL6C, which is my orange AP. And then you also start to see traffic pick back up on PAL6C. Some interesting adaptation behavior here when we disconnect and connect back to a new AP. But you can also see that we almost disconnected for about 20 seconds. And because Multiperf has that out-of-band management network, we're able to ping the link and start traffic back up. iPerf3 usually stops after 10 seconds and does not pick traffic back up. This is a new feature of Multiperf.
Thank you, Nandini, again. So let's move on to traffic emulation and bridging. As you guys know, in testing, we most often use emulated traffic flows. Essentially, we use applications that emulate the behavior of other applications. We do this mostly out of convenience. These tools are quite good. You know, they do a pretty decent job of traffic emulation. Of course, they oftentimes integrate statistics reporting that the application itself might not have. Now, this approach has its limitations. I mean, there are applications that are just either so new that they haven't yet been emulated, or they're just very difficult to emulate. Let's say a game, for example, where the traffic flow generated by a game might be dependent on the human playing that game. And so emulating that would involve emulating a human being, and that could be complicated, right? But you know, sometimes we just you know, these traffic generators, they give you a bunch of technical metrics. You know, in the case of video, it might be drop frames and blocking or what have you. Sometimes we just want to see the end result, right? And not rely on these metrics themselves. And so for that, you need bridging. Now, here's an example of how to do that in an Octobox testbed. Here we have, here in the lower left-hand corner, we have a smart TV, and it's watching content from Netflix from the internet. So we're using a real device, a real application, and real content, but we're still emulating the RF and the Wi-Fi aspects of this connection. So we're doing things like emulating distance, multipath. We can be generating interference, congestion, things that happen on the Wi-Fi layer. But we're doing it with the real devices, so we can actually watch the video as the emulation is happening. And of course, we're getting all these KPIs as well that we already discussed, even though these are non-octoScope test instruments. And of course, as we already mentioned, the PAL test instruments are really everywhere in the test bed. So the test bed is quite flexible to allow this application bridging. The PAL6 device is supported today. The StayPal test instruments, this feature is new. And so you'd likely have to buy a new version that has these Ethernet ports that are required for the bridging. Next, I'll hand it over to Steve Shearer. He'll be discussing some of the details of the multi-perf traffic generator, as well as he's going to do a wrap up for us for this session. Steve, go ahead.
Thank you, Yanni. So multi-perf now has endpoints for pretty much all the key devices that we see in the Wi-Fi arena. So we do iOS, we do Linux, we do Windows, we have Android, as you've seen in Nandini's demo. And what this means is that we can set up things like open air testing with loads and loads of consumer devices. So this image gives an idea of what some of that testing might look like. So the important thing is that we have the out-of-band management, which means that we can introduce disconnections. And when we introduce a disconnection, we do not have to run over to every single machine and restart the traffic generator. That is done for us. That out-of-band management also collects the statistics that are produced by the multi-perf endpoints, and it gives us the real-time plots, as you've seen as well. So we can do this in a combination of open air. We can do it in a test bed, obviously, but we can do combinations of that as well. So you could imagine running portions of a test in a test bed, coupled somehow to an open air testing environment. Makes it very versatile indeed. Just reminding that all of these guys are synchronized. So that allows us to align those statistics so we can display them. It also allows us to align any sniffer captures that we may have. So in a room like this, we may want to put 3 or 4 or perhaps even 5 sniffer probes. We want to make sure they're synchronized so that we can, combine their output. And the synchronization also allows you to measure one-way delay, which I think was one of the earlier questions. So let's take a quick look at some of the other features.
Steve, maybe I can interject here before you go to the next slide. There's a live question here from Kuiron. He's asking on slide 19. The question is, how does the TV actually connect to the StayPal? So the connection is provided through Ethernet. As I mentioned, the PAL6 instruments already have Ethernet connectors, and with the StayPal, this is a relatively new feature. But that's how it's done. So,
very good question, and it is a new feature, specifically because we find customers want to do exactly this type of stuff that Yanni was showing you. Multi-perf offers a very comprehensive set of features. If you sort of make a comparison with things like iPerf2 and iPerf3, they cover some of the bases. We leverage that and we provide full coverage. So you'll see some interesting new things planned on the roadmap, like isochronous traffic. We've talked about measuring one-way delay. We can actually produce histograms of one-way delay, which is very useful in analyzing delay performance. I think potentially the most important aspect, though, is this aspect of multiperf that does all of this statistics reporting. So we've touched on the management network, which is the network that synchronizes all of the devices, controls all of the devices, and collects all of the statistics back into the server. The great thing about that is, as Yanni mentioned, is you don't impact the traffic network. And there's a third network which we use for basically visualization. So the management network collects these statistics. The server will collate them into graphics and other forms, and you can then browse into that from a laptop or a PC without ever actually affecting the traffic on the traffic network. The other thing that I would like to point out is that multiperf, we've provided a Python API into it, so you can use multiperf in an interactive mode, as we've seen today, but you can also write Python scripts around that, and that makes automation a very straightforward to implement and a very powerful way of performing testing. So just in summary, we've talked about traffic generation. We've talked about the point that these days Wi-Fi networks are generally multi-point to multi-point. So you need a traffic generator that can handle that. One-way delay measurements are starting to become more important in the industry. And there are various ways to look at the results of those one-way delay measurements. That's supported by multiperf. We have iPerf2 and iPerf3 interoperability. So if you have some OS where we haven't ported multiperf to, there's probably an iPerf2 or 3 available for that, and you can use that in the interim. I think we provide the most complete set of statistics and metrics, ranging from, as you've seen, the common or garden throughput curves, but through MCS, through RSSI, and even some very detailed chipset level metrics as well. We've spoken about out-of-band management and how important that is. I think the point of being able to recover from link disconnections, we've touched on several times. It's actually a very important aspect, as you'll find out if you use a traffic generator that cannot recover. I just think of the open air testing slide that we looked at a little earlier. All of our stuff is synchronized. That enables, a number of measurements. It enables orderly data collection and so on. And there's now the ability to bridge traffic for video, for audio, and frankly, many other application layer metrics. So with that, I hope that you found this interesting.
Just to remind everybody that we do record these sessions. They're available on YouTube and as well as on our website. Here's all the links to the previous one. Just thank you, everybody, for attending. Thank you, Steve. Thank you, Nandini.
Thank you, everyone. Thanks.